Okay, so we have been looking at the different ways of presenting negative numbers, negative integers using our binary representation, and the last one we have been looking at was called number circle. So what was number circle? So if you remember, we looked into a 4-bit number circle where basically we presented all the numbers which can be presented using 4 bits in a circle, and we assigned them some index values. So for example, the 4-bit number circle contains numbers from 000 to 111, and we said that okay, this is the number circle we are forming. Now some interesting characteristics of this number circle is that we are starting from 0, and this is representing the number 0. We are incrementing it in the clockwise direction, and then till the number 0111, which is representing the number 7, we are incrementing like this. This is a continuous increment. But when the binary expression changes from 0111 to 1000, we said that okay, this number will represent minus 8. So essentially there is a break between this plus 7 and minus 8, and then the subsequent numbers are again incremented as we move in the clockwise direction. So from minus 8 to minus 7 and so on, and it ends at minus 1. So the unique thing about this number circle is that all the numbers are presented only once, or basically there is a one-on-one mapping for all the numbers which can be presented with this n bits. And also, like if we want to add two numbers, for example, let us say we want to add m with n, then we can basically identify m in the number circle. So in this case it is 5. So this is our m here, and if we need to add n, so let us say to start with, n is a positive number, let us say n is 2, positive 2. In that case we have to move clockwise this many steps to reach to our answer, which is 5 plus 2, which is 7. Alright. Now if this number n is negative, then there are two options. We can, to find the answer of m plus n, we can move counterclockwise n steps from m to get the answer. So basically 5 plus minus 2 will be, you move counterclockwise 2 steps from 5 and you will reach to the answer, which is 3. Another very important observation here is that I can reach to the same answer 3 by moving in the clockwise direction, but now I have to basically move how many steps? I have to move the total number of steps in the number circle minus whatever I am trying to subtract here, or whatever number I am trying to add here. So basically the number I am trying to add here is 2, the absolute value is 2. In the number circle there are 16 unique numbers. So the observation here is that if I need to add minus 2 with 5, so what I can do, I can move from 5 in clockwise direction. Now how many steps I should move? The total number of numbers in the number circle minus this absolute value. So 16 minus 2, that is 14 steps I have to move clockwise, in the clockwise direction, to reach to the answer. Alright. So basically I am dealing with 4-bit numbers. So 2 to the power 4 is 16, and I have to basically subtract the absolute value of n, which I want to basically add with the number I have, which is 5 here. So 16 minus 2 is 14. So now if I move in the clockwise direction 14 steps, then I will reach here, which is the answer. Alright. So this is a very, very important point, and we have to keep this thing in our mind. Alright. Now in this regard, in this number circle, we have a breakpoint here. So let us say if I want to add two numbers, which let us say 5 plus 5. In that case, I will see that 5 plus 5 will result in number, the answer is 10, but 10 is not there in our number circle. So basically it will create an overflow, and how to deal with this overflow we will be coming in our subsequent discussion. So basically, if the answer is too large or too small to be represented within this 4-bit number circle, then we call it an overflow, and to deal with that we have to see, basically we have to take some different measures. Alright. Okay. So now with this number circle in mind, so let us now move ahead and discuss about the 2's complement notation. So this 2's complement notation is one of the most important and very widely used notation for representing negative numbers. So 2's complement notation. Now what does this 2's complement notation says? So the 2's complement notation, I will just very briefly talk about the way we can mathematically represent the 2's complement number. So let us say this fu is the index, which is basically which is pointing to a number in the number circle. Okay. So in 2's complement method, a number u will be represented as the number u if it lies between if the number is positive, then it will be represented as u. All right. Okay. Now if the number is negative, so that means the number is lying between minus 2 to the power n minus 1 So if the number is lying in this range, then this number in the number circle will be represented by this index 2 to the power n minus the absolute value of u. So basically nothing but what we have seen in the number circle. So we are saying that a number u will be represented in the 2's complement notation by the same position as we have seen in the number circle if the number is positive. So we can look at the number circle here. So if the number is basically in between 2 to the power n minus 1 minus 1. So let's take one example. Let's take n, we are considering here as 4. All right. So 2 to the power n minus 1. So basically 2 to the power 3 minus 1. So if the number is lying between 0 all inclusive and 7, then this number in 2's complements representation will be directly represented by the index u. So if the number is, let's say, 1, then this is the representation of this number. Similarly, if the number is 4, then this is the representation. All right. So there is no problem, I hope. So we have drawn the number circle only. There is nothing new here. We have already discussed the number circle. Now, if the number lies between minus 8 and 0, basically and less than 0, then what will be the representation? The representation will be 2 to the power n minus the absolute value of u. So again, take an example. Let's say we want to represent minus 5. So what will be the representation in our number circle? So minus 5 will be represented as, so basically f of minus 5 will be 2 to the power n, which is 4 minus mod of minus 5. All right. So what it is? Mod of minus 5 is 5. So 2 to the power 4 is 16. So 16 minus 5, which is 11. Now what is the binary representation of 11? So basically it is 1, then 0, 8 plus 3, right. So this is the binary representation of 11. So this is what you see, which is represented as 5. All right. So now we are formally defining what is a 2's complement system. So we are saying that if the number is a positive number which is lying between basically which is lying between 0 and 2 to the power n minus 1 minus 1 all inclusive, then this number will be represented directly in its binary form. All right. If the number is a negative number, then the number will be represented by the binary form of 2 to the power n minus the modulo of basically the absolute value of u. All right. So we can look at some more examples. So for example, plus 4 in this 2's complement method will be represented by, so the 4-bit representation of plus 4, which is 0 1 0 0. If I want to look at the representation of minus 4, so how it will be? So we know that for minus 4 we have to go to 2 to the power n, which is 2 to the power 4 minus 4. So basically 16 minus 4, which is 12. And how do you represent 12 in binary? So basically 1 1 0 0, 8 plus 4 12, right? We can look at we have already seen 5. So 5 is 0 1 0 1, and minus 5 we have already seen that minus 5 is 2 to the power 4 minus 5, which is 16 minus 5 11, and the representation of 11 is 1 0 1 1. So this is how the 2's complement method, through 2's complement method we can represent the numbers. So basically we have just presented the numbers slightly in an organized manner compared to the number circle. So it's nothing but the number circle, it's the presentation is slightly different. Now what are the properties of this 2's complement method? So let's look at them. So properties of 2's complement method. So 2's complement notation. So here you see that the range of numbers which we can represent in this notation is basically minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So again we can look at the 4-bit number system which we have been looking at. So minus 2 to the power n minus 1, that means from minus 8 to 2 to the power n minus 1 minus 1, which is 7. So basically in the number circle, if you look at, so we have represented all the numbers from minus 8 to plus 7. All right. Now why it is only till plus 7? Because we have to accommodate also 0. So 0 is a positive integer, and that is why 0 to 7 is basically the positive numbers, and minus 1 to minus 8. So these are the negative numbers which can be represented by a 4-bit binary representation. All right. Okay. Now going forward, what are the other properties? There is a unique representation for the number 0. All right. So 0 in our 4-bit number system is represented as 0 0 0 0. So there is no ambiguity in the representation of the number 0. All right. Okay. Now there is another important thing which we should highlight here, is that the MSB or most significant bit of this 2's complement notation is equal to the sign bit. So MSB is equal to the sign bit. So see, we have collected so many different ideas. So we looked at the sign bit, then we looked into the concept of complementing in 1's complement method. Now we are combining all these methods, and we have seen that individually they have their shortcomings, but by combining all these characteristics we have now come up with this 2's complements notation, where the MSB is representing the sign bit. So if you look at the number circle, you see that all the positive numbers, so positive numbers are 0 1 2 3 4 5 6 and 7, all their MSBs are 0, which is basically consistent with the concept of sign bit. Now, if you look at all the negative numbers, their most significant bit is 1. So, this is also consistent with the introduction of sign bit in the binary representation. So, we see that a positive number in this 2's complement notation will always have MSB equal to 0. So, basically positive number, the MSB is equal to 0, and if the number is negative, then the MSB is equal to 1. So, these are the properties. So, remember what we all started with. We said that okay, there should be one-to-one mapping, and there should be unique representation. There should not be any ambiguity in the numbers, and there should be clearly we should be able to identify a positive number and a negative number. So, this sign bit will help us in doing that. All right. Of course, we have not looked into the arithmetic part of it, but we will look into that as well. So, to generalize, we can say that if we continue the discussion on the properties of the 2's complement numbers. So, basically we can represent every number in the range. So, every number in the range will be represented by minus 2 to the power n minus 1. So, basically for a 4-bit case, it starts from minus 8 to plus 7, right. It has a unique mapping. So, has unique mapping, and that means basically there is a unique point in the number circle. So, the number circle is very, very important, as basically this is the representation of 2's complements method. All right. Now, can we represent all the numbers uniquely? If the number is within this range, then of course we can represent every number uniquely. But what if basically the number is greater than that? So, in that case we can say that okay, so let us take a number, let us say take this number 3. Now, if I add with 3 2 to the power n, what do I get? I get 19, 3 plus 16, which is 19. So, the number 19 in this number circle will be also represented by this number only. So, basically we can say that a number a, which for our 4-bit number system will consider as equivalent to b. So, this 3 horizontal lines is basically it is the equivalence sign, and it means same point on the number circle. All right. So, basically it means that a is equal to b mod 2 to the power n. I hope you guys are all familiar with the operator mod. So, basically it's the remainder. So after b mod 2 to the power n means b divided by 2 to the power n, and whatever is the remainder, that is the answer. So if let's say in this case, if we consider the example of b equals 19, or let's say a is 3, b is 19. So we can say that 19 is nothing but this can be also expressed as a is equivalent to b, because 19 mod 2 to the power n, which is 4 here, 2 to the power 16. So 19 mod 16 is equals to 3. So that's why a is equivalent to b. So they represent, or they point to the same point in the number circle. All right. So continuing with this, we can also say that the number, a negative number minus u on the number circle is nothing but 2 to the power n minus f of u. So basically, if I take any negative number, so minus 5, so which is nothing but 2 to the power 4 minus your basically the positive number, which is 5. So basically I'll just write down again. So f is minus 5, so 2 to the power 4 minus 5, which is 16, minus 5, which is 11. And if you look at the number circle, 11 is represented as 1011, and that is the representation of minus 5 in the number circle. All right. Now since to find the number, we are subtracting it from 2 to the power n, that's why it is called 2's complement method. All right. And just to reiterate this thing, where from this came? This came because this representation. So the if you look at the number circle, so this f of minus 5, I can reach here by moving basically from so from, let's say, from 0, if I want to, from 0 if I want to okay. So let's say from 0 I want to reach here. So how can I reach? I can move in the clockwise direction 2 to the power n minus 5 steps, which is nothing but 11 steps, or I can move counterclockwise 5 steps. So basically, if I move counterclockwise 5 steps from here, so okay, sorry, it might not have been visible. So what am I saying? That if I want to represent this number minus 5, so I can start from 0 and I can move 2 to the power 4 minus 5 steps. So that means 11 steps in the clockwise direction to reach here, or I can reach at the same spot by moving counterclockwise 5 steps. So this is the beauty of our number circle. All right. Now what are the advantages? So we have seen most of the properties of this 2's complements notation and its advantages, etc. But how about the arithmetic operations? Like remember, one of the primary concerns for this negative number representation was that the arithmetic operations should be very easy to perform and there should not be any error in our arithmetic operations. So now let's look at how simple arithmetic operations can be performed using this 2's complement notation. So let's say I want to add two numbers. So the numbers are 2 and the other number I want to add is -4. All right. So what are the notations? So 2 is represented as this. How about -4? So -4 we know. So please keep practicing this. So 2 to the power 4 minus 4, which is 16 minus 4, which is 12, and the binary representation of 12 is 1100. So this is the binary representation. Now if I add these two numbers, so now we need to add these two numbers. So 0010 and 1100. So basically if I add them, so 0111. So we get the answer as 1110. Now what is this number? So this is the binary representation of 8 plus 4, 12 plus 2, 14. So what is 14? So 14 is nothing but 2 to the power 4 minus 14 which is 2. So 2 means this is representing -2, right? So on the number circle I got a correct answer. I hope this is clear. So essentially if I want to design an ALU, so if the ALU can perform addition operation, then using the 2's complement notation I will be able to do subtraction as well, because in that case the number I need to subtract, I have to represent it in 2's complement notation, and then if I do simple addition, then it will be basically giving me the correct answer. So this is very, very important. All right, and there will be lot of examples, etc. in your tutorial, as well as we will try to share some practice problems. So you can verify this, that this 2's complements method notation actually works for representing any arithmetic operations. Similarly, you can look at so I'll not go into too much detail. So basically just for completeness I can say that, okay, if you want to add two numbers and if one of the number is negative, then you have to represent that number into its 2's complement method. So so that means let's say f of u you want to add with f of v, and v is a negative number. So basically you have to represent v as 2 to the power n minus v, which is the mod of v, and that will give you the actual outcome. Now in some cases, for completeness, it might happen that your result is not fitting into the number circle. So basically the result is not containing, or you can't find the unique mapping in the number circle. In that case, so what you have to do, or if there is an overflow as we discussed, like if the number is bigger than this, then you have to basically also take the mod of it with 2 to the power n to find the actual result. So that will give you the answer of f of u plus v, where v is a negative number. All right. Similarly, you can also do some quick checks. Will for multiplication, will it hold? So take this example. So let us say 2 multiplied by minus 3. So for this multiplication, so we have 2 represented as 2. What is the representation of minus 3 in the number circle? So I am just basically doing it quickly, so you can verify it. So minus 3 in the number circle is represented as 1101. So 1101 is nothing but 8 plus 4, 12 plus 1, 13, right? So 2 multiplied by 13. Okay, so the binary representation of minus 3 is 13. So the answer is 26, right? So you can do the multiplication and check that, okay, 2 multiplied by 13 will give you 26. Now 26 is not in this number circle, so to find out the equivalent, we have to do a mod of 16, and that will give me, what is the remainder? 10. Now what is 10 in this number circle? So 10 in this number circle is 101, basically 1010, which is nothing but minus 6. So basically you get your answer for multiplication also. All right. So it says that you can do all the arithmetic operations, and the beauty is that you don't have to change at the hardware level too many things to achieve this. All right. Okay. So how do we find 2's complements of a number? So if this number circle is in front of us, then we can easily find this, but otherwise, like whenever we get a negative number, we have to basically do this operation 2 to the power n minus u. So where u is the number which we want to represent in 2's complement. So for example, again minus 4, if I want to find out what will be the 2's complement representation, so I will have to find out, like okay, 2 to the power n, which is 16. If I am talking about 4-bit number, 16 minus 4, which is 12. So the binary representation of 12 will be the 2's complement representation of minus 4. So is there a easier way of computing this? So basically computing this 2's complement, so 2's complement representation is given as 2 to the power n minus u, which I can also write like 2 to the power n minus 1 minus u plus 1. All right. I have not done anything different here. So I have just added 1 minus shown 1 minus 1 here and added again plus 1. So this, they will cancel each other. So I have not changed the number. Now do you guys remember where you have seen this thing, 2 to the power n minus 1 minus u? this is nothing but the 1's complement representation. So, whenever I have an n bit number, if I just flip all the bits, I am doing this operation only, alright. So, this is our 1's complement representation, which is nothing but flipping all the bits or complementing all the bits. And if I just flip all the bits and add 1, that should give me my 2's complement representation. So, this is much faster compared to doing this operation, alright. So, I can quickly find out 2's complements of any number by flipping all the bits and then adding 1, alright. So, basically let us say I have this number 0 1 0 0. So, the 1's complement of this number is, you flip all the bits 1 0 1 1. Now, what is the 2's complement of that? You add 1 to it. So, basically then it becomes this. So, the number 0 1 0 0, its 2's complement expression will be this. Basically 4 is represented as, in the 2's complement method, as 1 1 0 0, which is, you can verify here. So, minus 4 is 1 1 0 0 and this is your 4, alright. So, this is the quicker way of representing the 2's complement number. Now, there are a couple of interesting things which we need to go over. So, the next thing we would like to go over is called sign extension. So, basically what this means is that, let us say I have an n bit number and I want to represent it, or I want to convert it into a m bit number in the 2's complements representation. So, the objective is convert a n bit number to a m bit number. So, m bit 2's complement number. Now, here basically m is greater than n. So, let us take example. So, let us say m is 8 here and n is 4. So, I have a 4 bit number and I want to represent it in in 8 bits in the 2's complements representation. So, if the number is positive, then it is very easy, as many of you can guess, that you need to just add m minus n zeros. So, basically add m minus n zeros in the MSB position. So, example can be, let us say I have a number plus 4, which is represented as 0 1 0 0 in my 4 bit representation, and I want to convert it to an 8 bit representation. So, what I will do, I will add m minus n zeros. So, basically m minus n is 4. So, I will add 1 2 3 4 zeros followed by the number. Okay. So, the number remains same, there is no ambiguity, nothing, alright. How about negative numbers? If this number is negative, Now we know that a negative number in an n bit number system is represented as 2 to the power n minus this number, the mod of this number, alright, in n bit number system. Now we have to find out how it will be represented in m bit number system. So in m bit number system, let us say it is represented as f dash u, and the representation is 2 to the power m minus u. So we have to find out the relation between this f of u and f dash of u, this mapping, alright. So if you think little bit, it should not be too difficult. So here let us say we take this example. So we have a 4 bit representation of minus 4, which is 2 to the power 4 minus 4, which is 12, and the representation is 1100. I want to represent the same number in 8 bit. So it will be nothing but, with the same way if I go, it will be basically 2 to the power 8 minus 4, alright. Now what is this 2 to the power 8 minus 4? So to calculate that 2 to the power 8 minus 4, it will be nice to know what is the difference between these two representations. So just to find out the difference, what we can do, in one representation, let us say for the 8 bit representation we know it's or m bit representation, it's 2 to the power m minus u, and in the n bit representation it is 2 to the power n minus u, right. So this is essentially the difference between these two representations. So what is this difference? This difference is nothing but 2 to the power m minus 2 to the power n, right. And what is it? 2 to the power m minus 2 to the power n. Take another a small example, maybe 2 to the power 4 minus 2 to the power 2. So 2 to the power 4 is 16, which is this, and 2 to the power 2 is this, right. All right. So it is nothing but 1100. Does this make sense? All right. So if this makes sense, then okay. So okay, so this is nothing but 2 to the power n plus 2 to the power n plus 1 plus so on 2 to the power m minus 1. So basically you will have all ones till 2 to the power m minus 1. So it can be also represented as So it can be also represented as 1 1 1 1 and so on, and then 0 0 0 0 and so on. So here the number of zeros are n and number of ones are m minus n. Alright. So basically I can find out the 8-bit representation of minus 4 by writing down m minus n number of ones. So m minus n is 4, so 4 ones followed by n zeros. So basically these 4 zeros plus the 4-bit representation of the number. So 4-bit representation was basically 2 to the power 4 minus 4, alright, which is nothing but 1 1 1 1. And what was this representation? This is 1 1 0 0. So 1 1 0 0. So basically the 8-bit representation of the number 4 is this, and you can verify that this number is nothing but 2 to the power 8 minus 4. Alright. So I will leave it to you to prove that this is exactly as 2 to the power 8 minus 4. Okay. Alright. So another easier way to basically convert it is, you see that you have just extended your sign bits by the number of additional bits now you have. So basically earlier you had 4-bit representation, now you have 8-bit representation. So you have just extended your sign bit that many times, 4 times, because you have now 4 additional bits. So this is how you can extend your basically number of bits if you need to. So the sign extension, if we want to summarize, so to convert a negative number, you have to add m minus n ones in the MSB position. Alright. And you can extend it further. You can say that, okay, in both cases, whether the number is positive or negative, in both cases extend the sign bit bit by m minus n positions. Alright. So now if you are given a negative number in let us say 1101 and you need to represent it in 8 bits, then you know that you have to add 4 ones in front of it. Similarly, if you are given a positive number like 0100, you have to add 4 zeros in front of the number to convert it into a positive number. Alright. Okay. So I hope this makes sense. Now the last thing we would like to discuss about the negative integers is the overflow theorem. So the overflow theorem says that if you need to add two numbers u and v, and this number u and v are such that the product of u and v is less than 0, then there will never be an overflow. So basically it says that there will never be an overflow. you can verify this. Take some examples. Again we can look at the number circle. So let us say it says that uv less than 0, that means one has to be positive, another has to be negative. So take maybe extreme cases. We can think of let us say number the highest number in okay, so this okay, we can take this -8 and let us say another number is 7. Okay, so 7 into -8 is 56, -56, so it is less than 0. Now it says that you will never have a problem of overflow if you need to add these two numbers. So -8 plus 7, so basically you can go in this number circle to find out what will be the answer. So it is -1, so it is within the range. Similarly, you can take any number and you will see, you can take other extremes like very small number, one small number, one large number, and you will see this condition always is met. Now we can also look at the cases when there is an overflow. So let us say I want to add two numbers, 5 with 5. So 5 plus 5 is 10. Now this number is not on this number circle. So then there is an overflow. So wherever you cross the breakpoint, then there is a overflow. So if you cross the breakpoint, then only there is an overflow, and this can happen if u into v is greater than 0. So in that case an overflow is possible. All right. So if u and v are greater than 0, then there is a possibility of overflow. As we mentioned, like 5 plus 5 will create will result in an overflow. And just for completeness, we can look at a smaller number circle and see this example of extreme cases. So let us say I have a only 2-bit or 3-bit number system. So my number circle now has 0, 1, 2, 3, and then there is a break. This is -4, -3, -2 and -1. All right. So in this case, let us say my u is 1 and v is -4. All right. So will it result in an overflow? So u and v results in -4. So u multiplied by v is -4, so it is less than 0. So if I add these two numbers, -4 with u, then it is -3, so there is no overflow. So there is no problem. So basically it basically proves the point that there will be never an overflow if u v is less than 0. Now u v, if they are of the same sign, so when there can be an overflow? If u and v are greater than 0, that means they are of the same sign. So that means u and v are of same sign. All right. If that is the case, and then the result which you are getting by adding u plus v, So basically, if you get a result or the sign of the result is different from the sign of u or v. So basically, if the sign of the result is different from the sign of u or v, then there is an overflow. So we can check this. So we are saying that u and v are of same sign and the result we are getting has a different sign than what u or v has, then there is an overflow. So take this example of, let's say, two numbers which are, let's say, 3 and 2. So if I want to add 3 and 2, so both are positive, but the answer I get, so basically if I add 3, basically with 3 if I add 2, so basically I have to move in the clockwise direction on the number circle. So I'll be ending up here. So I'll move 2 steps. So the result is -3. Now you see that the result we are getting has a different sign than both u and v. So that is a problem. All right. So that indicates there is an overflow. Similarly, we can take another example of negative numbers. So let's say -4 and -3. If we add them, then what we are supposed to get? So the result is supposed to be, so from -4, if I add -3, so what I'll do? I'll be, so -4 is here. So -4 and I want to add -3, which is 2 to the power n, which is here 3. So 2 to the power 3 minus 3. So this is 8 minus 3, 5. So basically I will be moving 5 steps in the clockwise direction. So 1, 2, 3, 4, 5. So -3 minus 4, the addition result I am getting is a +1. So the sign of u and v are same, but the result I am getting has a different sign. So this indicates that I have already encountered overflow and the result is not correct. So basically you have to have some mechanism to detect this overflow and basically make sure that you do the correction. All right. So this is what is meant by overflow. So we will break here and then continue our discussion from here. Thank you.